Welcome to the second lecture of this week. So far in the time domain analysis, we have seen the so-called transient response characteristics. So we have seen characteristics of the systems until a convergence happens in the response. And these parts are called the transient part of the response. And in this lecture, we are going to see the final part of time domain analysis, which is called the steady state response. And in steady state response, we are going to be looking at the performance of systems when the responses actually converge to some final behavior at the end of the transient. So today's topic is going to be the so-called steady state error. So I would like to introduce this concept by reminding you what we have done in this respect at the beginning of the at the beginning of time domain analysis. So suppose that we have a mass with mass equals to 1 kilogram, and suppose that I give the mass the force input F, and suppose that the output is V equals to X dot. Okay, measured in this direction. So remember the mathematical model of such a system. So m times v dot is equal to f. This is our system, and since m is 1, I can actually neglect this. So I have v dot is equal to f, and if I look at the transfer function, g of s is going to be output divided by input Laplace transforms, and it's going to be just 1 over s. Okay? And at the beginning of time domain analysis, we learned how to control the velocity of a mass by using a proportional controller. So I connect this system in a feedback loop, which is given like this. So this is my f, and this is my output V. Okay, and this is the reference input. And this is a proportional controller whose gain is just equal to K. And I have defined at the beginning of time domain analysis 1 over T as the K. And T is the parameter of the system. And when we did the analysis of such a system, we have seen that T turns out to be the time constant of the response, of the step response at the end. Okay? So remember, we have found the closed loop transfer function in this case. G closed loop of S was equal to, I have the forward path transfer function divided by 1 plus everything in the loop. Okay? So we have something like this, and I have 1 over Ts plus 1 as the closed loop transfer function of the system. Remember, I can actually write this as 1 over T and S plus 1 over T, and we see that the pole of the system is at minus 1 over T here. This was a first order system that we have considered, and we have seen that the step response and the ramp responses of such a system. So when we look at the step response of the system, this is the step input given to the system, which means that we want the velocity to be equal to the reference constant, which is 1 meter per second. And in that case, we have seen the response, the step response would reach the final value, desired value, 1 here. So in that case, remember, we said that this system has a steady state error equal to 0. What was the steady state error? We called this signal after the subtraction operation as the error signal. Okay? So E of t was defined as the error signal, and you see that the error signal is the difference between the reference signal and the output of the system. Okay? And we see that this is my R of t and this is my Y of t, and we see that this difference as time goes to infinity goes to 0. Okay? So before this convergence happens, we call the response as a transient response. Before a significant convergence happens, and when this convergence happens, we call the response as steady state response. Okay, so far in the time domain analysis, we have considered only the transient response characteristics. What is the speed of this convergence, and what is the settling time, what is the rise time, etc. They are related to all the transient response characteristics. And when we look at the steady state response, we have to consider this part of the response where convergence actually has happened to some final behavior in the system. And in this case, we have seen that since this difference is equal to 0 between the reference and y, as time goes to infinity, this system has a 0 steady state error. We show the steady state error with the letters ESS, and for this system and for this input, the steady state error is equal to 0. So I define the steady state error as limit as time goes to infinity, the error signal E of t. All right? And in this case, for the unit step input, this system has 0 steady state error, which is a good thing for us. We would like the systems to have 0 steady state error, or we would like the systems to have small steady state errors in magnitude. All right? And remember, the next topic was the ramp response of the same system. And this was the ramp input for the system. And we looked at the ramp response of the system, and it looked like something like this. And we saw that there was always a difference remaining between R of t and y of t in this case. This y of t was never converging to the R of t exactly. There was always a finite difference, a non-zero finite difference between the output and the desired response in the case of a ramp input. In that case, of course, this difference was not equal to 0, so we said that the steady state error, it was not equal to 0 in that case. Okay? So remember what we did so far in time domain analysis. Here again we have a transient part of the response, transient, and we have again a steady state part of the response. Okay? And remember what we did in the transient part. We tried to obtain these characteristics, these response characteristics, like the settling time, for example. We have tried to learn what the relationship between the settling time and the Laplace domain quantities. So the topic of this lecture is going to be obtaining the relationship between the steady state error and the Laplace domain quantities. Okay? So, for example, the pole location was important for the settling time. If the pole is close to the imaginary axis, settling time is larger. So similarly here, if the pole location is close to the imaginary axis, the settling time, the time that passes before we converge to this constant difference behavior actually becomes larger. So now we would like to understand the relationship between the steady state error, in this case it is 0, and in this case it is non-zero, and the Laplace domain quantities, for example, the pole locations or the parameters of the Laplace domain quantities like t, etc. Okay? So that is the topic of this lecture. So what we're going to mainly do is that we're going to ask the following question. Can we determine steady state error in Laplace domain? And the answer to this question is going to be, of course, yes. So here I see that the steady state error is nothing but the final value of a signal. I have the signal E of t, and its final value is the steady state error. Remember, at the beginning of the semester, we have seen a Laplace domain property that is called final value theorem. So we are going to actually apply final value theorem to the concept of steady state error, and we will try to make a connection between the steady state error and the Laplace domain quantities. So I'm going to start with the generic case first. So suppose that I have a feedback system given in the following form. I have this G of S and I have this H of S in the feedback path. Okay? So this is my reference signal, this is output, and this is my error signal, E of t. We always define the steady state error as the final value of E of t. Okay? So E steady state, I will write the same thing actually, is the limit as time goes to infinity, E of t here. And if I want to make a connection between the Laplace domain quantities and the time domain quantities, the E steady state is a time domain quantity because it is the limit of a function of time. And if I want to make a connection between Laplace domain quantities and E steady state, then I need to use the final value theorem. Remember, the final value theorem tells us that this limit, if some conditions are satisfied, we are always going to assume that those conditions are satisfied in this course. And I will say that this is limit as s goes to 0, s times Laplace transform of E of t. Okay, which is E of S. So this is my final value theorem coming from the Laplace domain properties, and therefore we are going to be using this property in order to be able to make a connection between this time domain quantity and the Laplace domain quantities as E of S. All right? So of course this is not all. I am first going to write E of S in terms of this input and this transfer function parameters G of S and H of S, and then we are going to be making a connection between the input type and the transfer function parameters of G of S, H of S, and this time domain quantity, the steady state error. So the first thing that I'm going to do is to calculate what E of S is. In this case, I know that the closed-loop transfer function for such a system would be as follows. The closed-loop transfer function is the forward path transfer function divided by 1 plus everything in the loop. G of S, H of S. Okay? I know that, so this is my overall closed-loop system. And here I know the relationship between the Laplace transform of the input and the output for this system. And the relationship is Y of S is equal to G closed loop of S times the Laplace transform of the input. Okay? So I have this relationship. Now I want to make a connection between E of S and the input here, R of S. Okay? What is the transfer function between E of S and R of S? In order to be able to find that, I will use the following relationship. We see here that E of t is the input of this system and Y of t is its output. So I have also the relationship Y of t is equal to G of S times E of S. Okay? Y of S is at the same time G of S times E of S. So here, first I have used the overall system, and the input of that overall system is the reference signal, and the output is the Y of t, output of the system. So now I have written the first equation from that one, and the second equation uses just the equation for the forward path transfer function here. This G of S has input E and the output signal is Y. As a result, if I multiply G of S with the Laplace transform of E of t, G of S, E of S, I would obtain Y of S. Now from these two equations, I can actually try to extract what E of S would be in terms of R of S. Okay? So I see here that E of S is equal to Y of S over G of S. That is my second equation here. And if I use the first equation here, G closed loop of S, R of s divided by G of s here. And if I write the G closed loop of s here, if I use this, I would get G of s over 1 plus G of s H of s divided by G of s times R of s. When I cancel these G of s's, I would get the equation that I'm looking for. Okay? So this gives me E of s is equal to 1 over 1 plus G of s H of s times R of s. Okay? This is the relationship between the reference input, which can be unit step, unit ramp, etc., and the error signal E of s. Okay? If I use this final value theorem, then on that expression, then I'm going to get the following. So the steady state error is equal to limit as s goes to 0, that is coming from the final value theorem, s times E of s. That is what that theorem says. S times this thing. So s, I have R of s here, divided by 1 plus G of s H of s. Okay? So this is the main result that we are going to be using. So that is the result that we are going to use in this lecture. All right? And it tells us that the steady state error is related to the reference input Laplace transform and the system parameters by this limit. Okay? And here you see that these parameters of the system, G of s, H of s, enters into this limit only through the multiplication G of s, H of s. Okay? So this multiplication is really important for the steady state error. And that is why we are going to give a specific name to that multiplication. So G of s, H of s in the control literature is called the open loop transfer function. Okay? That is the name of this multiplication. So when you look at this system, sometimes students think that open loop transfer function is just the transfer function G of s. It is not correct. Open loop transfer function is what you obtain when you open this loop and hold it like a wire from the start to the end. Okay? G times H is called the open loop transfer function in the control literature. So we are going to see that the steady state error is going to be closely related to the properties of the open loop transfer function. So when you look at a feedback system like this, you can directly see what the open loop transfer function is by multiplying the feedback and the forward path transfer functions. And by looking at that multiplication, then you would be able to say what the steady state error of the system would be to some simple input like unit step or unit ramp. So let us make a definition. Let the open loop transfer function, I'm actually going to abbreviate this open loop transfer function with the letters OLTF. Let the open loop transfer function G of s, H of s be written as follows. So G of s, H of s is equal to, there is a scalar parameters and I have s to the n in the denominator and I have tau 1 s plus 1, tau 2 s plus 1 going until tau m plus 1, s plus 1, and I have in the denominator t1 s plus 1, t2 s plus 1 going until tn s plus 1. Then the closed loop system is called type M, where n is the number of integrators. An integrator is just 1 over s in Laplace domain. Remember, multiplication with s is the derivative in Laplace domain, and the division by s, which is 1 over s, is called an integrator in Laplace domain in the open loop transfer function. So this is our definition of the type of a system. Okay? Now we are going to try to understand what this means. So we are starting with an open loop transfer function, and we are assuming that open loop transfer function can be written in this form. This form in control literature is called the Bode form of the transfer function. And any rational transfer function can be written in this Bode form. I will try to show you how we can do that. So suppose that you have a system given like this. So suppose that I have 1 over, so let me say here, s plus 2, and I have s plus 3 and s here. And let us say here, in the feedback path, I have 1 over s plus 4. Okay? So this is just a closed loop system, and we are interested in the steady state error of such a system. What would be the limit of this signal e of t as time goes to infinity? In that case, I would need to know what the open loop transfer function of this system is. So the open loop transfer function, if I write g of s, h of s, it would be looking like the following. This is my g of s, or whatever on this path is going to be forming g of s, and whatever on this feedback path would be forming the h of s. G of s, h of s for this example is going to be the multiplication of these terms here. S plus 2 divided by s, s plus 3, and s plus 4. All right? So now, do you think this transfer function, this open loop transfer function, do you think it is in Bode form? Your answer should be no here, okay? Because here the terms are like here s plus 2. So here the terms are, in this case I have, in the general form I have m zeros, and I have n poles like this, and I have capital N poles at 0 as well. So now let us try to put this transfer function in Bode form. Okay? How can I do that? I need to make the constant terms here equal to 1 in both the numerator and the denominator. Okay? So here I have a k parameter, g of s, h of s. I will calculate what k is, but before that, let me put this term s plus 2 into this form. How can I make the constant term here equal to 1? I can just take 2 parentheses. So here, in 2 parentheses, I have s 1 over 2 times s plus 1. Okay? So you see that in this case, this term, 1 over 2s plus 1, is exactly in the form of the term in the parentheses here. So tau 1 here is 1 over 2, and I have the term 1 here, constant term 1. All right? Divided by, I will leave this s term where it is, s, and I will take 3 parentheses here because I want to put this term in the parentheses also into its Bode form. I want to make the constant here equal to 1. So I will take 3 parentheses here. I have 1 over 3 s plus 1. Now this is exactly in this form. And I will take 4 parentheses in the last term here. For 1 over 4s plus 1. Okay? So here I will collect all of the constant terms into a single value. It is going to be 2 over 3 times 4. It is going to be 1 over 6. divided by s times 1 over 2s plus 1 divided by 1 over 3s plus 1 divided by 1 over 4s plus 1. Now, you see that I have brought the original open loop transfer function, which is given like this, which is not in Bode form, into Bode form. Okay. Now I have tau 1 is 1 over 2, t1 is 1 over 3, and t2 is 1 over 4, and I don't have any other t terms here. And I have only one term in the numerator, and I have two terms, double terms in the denominator. Okay. Now, what is n here? What is this capital N for that open loop transfer function? Here we say that the closed loop system is type n if the open loop transfer function contains n 1 over s terms. Okay? 1 over s terms are called integrators in the control literature, and I have here the number of them in the open loop transfer function gives us the type of the closed loop system. We are defining here some quantity called the type of the system, some property of the system, which is going to be important for us, and that is the type of the system. We call the system type capital N if there are n 1 over s terms in its open loop transfer function. So here I see that this capital N here is 1 here. Okay? So therefore here we have a type 1 system in this case. Okay? So this system, this closed loop system is a type 1 system, because in its open loop transfer function we have only one 1 over s term, okay, which is this one. So now, why is this Bode form important? So you see here that when I let s go to 0 on this right hand side here in this expression, when I let s go to 0, I will let s go to 0 in g of s, h of s. And in this g of s, h of s, if I let s go to 0, each of these terms in the parentheses will go to 1. So they won't affect the result of this limit. So when s goes to 0, substitute s equals to 0 here, and this term will bring 1. Substitute s equals to 0, this term will bring 1. Similarly, for all these terms, the limit will be 1. So these terms will not affect the steady state error of the system when I let s go to 1 in that expression. So the only terms that will affect the steady state error would be this k parameter and would be this s to the capital N parameter. So here, when I let s go to 0, this term would bring 2, this term would bring 3, this term would bring 4, etc. But when I look at the Bode form transfer function, I see that these terms would all bring 1 to me when I let s go to 0, and these terms would not affect the steady state error at all when I try to make that calculation. Okay? So the only terms that will affect the steady state error terms would be this k. In this case, k is equal to 1 over 6 and n, which is 1 for this example. So the type concept is really an easy concept. So you just count the number of 1 over s's in the open loop transfer function. So suppose that you have a system given like this. What is the type of this system? So first look at the open loop transfer function. G of s is 1 over s plus 1 and h of s is 1. So this is a unity feedback system. So h is 1. So g times h is 1 over s plus 1. GH, the open loop transfer function is 1 over s plus 1. What is the type of this system? So I see that I need to count the 1 over s's in that transfer function, and there is no 1 over s in that transfer function. Okay? That means that this system is a type 0 system. Okay? as I said, it's very easy to determine the type of the closed loop system. So suppose that I have 1 over s plus 1 here, and suppose that I have 1 over s plus 2 here, and suppose that I have 1 more s. What is the type of such a system? Just count the open loop transfer function 1 over s's. Multiply this term with this term and count how many 1 over s's you have there. And it's going to be 2 in this case. That means that this overall system is a type 2 system. Okay? So we have a very, very similar, very, very simple concept. Now we are going to actually consider the steady-state errors of systems to different simple inputs. Like what would be the steady-state error of a type 0 system to unit step input? Or what would be the steady-state error of a type 1 or type 2 system to a unit step input or to a unit ramp input? So now we are going to investigate these steady-state errors to unit step, and then we are going to go into 4 different types of systems, and then we will go into unit ramp, and we will have a third simple input function, which is going to be called unit acceleration or unit parabola function. It is just going to be another simple input, and we are going to investigate each case separately. So now let me look at these. So I will erase this part so that I have more space. So steady-state error to unit step input. Okay? I'm always going to be using the same theory here. Okay? This is my theoretical equation expressing the steady-state error of the system to expressing the relationship between the steady-state error and the input type and the system parameters here. Now, what would happen to R of S when we have a unit step input to the overall system? To this system, if I have R of t is equal to the unit step input, then I would have just R of s equals to 1 over s, which is the Laplace transform of the unit step. R of s is going to be 1 over s, and then I will substitute it into this equation. Okay? So in that case, the steady-state error is equal to limit as s goes to 0. I have s times R of s. R of s is 1 over s divided by 1 plus g of s, h of s. So these s's are going to cancel each other, and I will end up with limit as s goes to 0, 1 over 1 plus g of s, h of s. Okay? Now we see that in this function, the only s-dependent terms are coming from the open loop transfer function. Therefore, I will take this limit to the denominator, and I will write this is equal to 1 over 1 plus limit as s goes to 0, g of s, h of s. Okay? We will actually call this limit of the open loop transfer function as s goes to 0 with a specific name. And that specific name is going to be the static position error constant. So, and the name of that coefficient would be Kp. Okay? So the steady state error to unit step input is going to be given by this formula. Where Kp is the following. So the steady state error to unit step input is steady state is 1 over 1 plus Kp, where Kp is limit as s goes to 0, g of s, h of s. So the limit of the open loop transfer function as s goes to 0 is called Kp, and the name for Kp in control literature is static position error constant. Okay? That is the name given to this constant. Okay? So when we look at such a transfer function, what is Kp? So in this case, I will just let s go to 0 in this open loop transfer function. If I let s go to 0, all of these terms would go to 1. So I would have 1 over 6 divided by s. Let s go to 0 and this becomes infinity. So this static position error constant can be sometimes infinity. It is going to be sometimes equal to 0, it is going to be sometimes equal to infinity, and it's going to be sometimes a non-zero, non-infinity number. Okay? So for this example, we have infinite static position error constant. And what about this example? In this case, GH is here 1 over s plus 1. And I see that if I let s go to 0 here, I would obtain just 1. So the static position error constant for this system is just equal to 1. That means that the steady state error for that system to unit step would be 1 over 1 plus Kp is 1 over 2. So the steady state error of this system to unit step input would be 1 over 2. Okay? So now we are going to be comparing the steady state errors of different types of systems to unit step input. So I will write here the type of the systems, I will write here the Kp of the system, and I will write here the steady state error of the system for different types of systems. I will consider the type 0, 1, 2, 3, etc. Okay? So when I try to fill this table, I am going to assume that we have the generic form of the open loop transfer function, which is given like this. Okay? Now let us look at a type 0 system. If I have a type 0 system, then my open loop transfer function would be looking like this. But what is going to be the important thing? This capital N will be equal to 0. So when I have a type 0 system, I won't have this term. All right? So then what is Kp for a type 0 system? It is the limit of this GH as s goes to 0. So I know that if s goes to 0, all of these terms in the parentheses will go to 1. So they won't affect my limit. So this term is non-existent for a type 0 system. As a result, this limit is just going to be equal to k for a type 0 system. So Kp is equal to k for a type 0 system. And then what is the steady state error? It is 1 over 1 plus Kp. So it's going to be 1 over 1 plus k here. If this k is large, then the steady state error will be small. And if k is small, the steady state error will be large. So now let us look at a type 1 system. This system, this example system that we have already considered here, is a type 1 system. And we have seen that Kp of that system was infinity. So we can see the same thing here as well. For a type 1 system, I will have k over s here. K over s, n is 1, and all of the other terms are possible. Okay? Now let us try to take this limit. So when I take the limit as s goes to 0, all of these terms would go to 1, and I would have k over s as s goes to 0. Okay? In this case, I would therefore have the Kp equal to infinity. And what about the steady state error in that case? If Kp is infinity, I need to substitute here infinity. 1 over 1 plus infinity. 1 plus infinity is still infinity. And if I divide 1 by infinity, I would get 0. So we see here that if a system is type 1, if in its open loop transfer function, if it has only one 1 over s term, then its steady state error as time goes to infinity is going to be 0. Okay? Let us look at type 2 system. For a type 2 system, I have s squared here. k over s square and the other terms. The other terms as s goes to 0 would go to 1, and I have k over s square as s goes to 0. K over s square would still go to infinity as s goes to 0, and I would have an infinite static position error constant. And I have the same result of 0 steady state error for a type 2 system as well. So similarly, if you continue in this manner, you would see that the Kp is infinity for all these higher type systems, and I would have a 0 steady state error for such systems. Okay? And they are going to continue in this manner. So the system, for a closed loop system, to give steady state error, 0 steady state error to unit step input, its type should be at least 1. It can be type 2, type 3, but the type should be at least 1 as and if it is type 0, then it's going to have a non-zero but finite steady state error to unit step input. So now let us try to look at these response types. So when I look at the response of a system, I might have this is my unit step, that is the reference input. What would the response of a type 0 system be looking like? Okay? What would the response of a type 0 system look like? In that case, I would just have this type of response. For a type 0 system, the steady state error is non-zero but finite. So we see here that my response for a type 0 system might be looking like this. Just this. Okay? So we have a non-zero difference between the step input and the final value converged by the response. Or it might be something like this. So we see here that there is again a so the difference can be negative in that case. So if k is negative, for example, in that case I can have 1 plus some negative large number. In that case, the steady state error might be negative. Okay? And in that case, I would have this type of scenario. Or the response might be an oscillatory one. So still a type 0 system, but the convergence might be to a value given like this. Okay? So these are the case for a type 0 system. It has non-zero but finite steady state error. So now I can look at type 1 systems. In that case, I know that the steady state error will be equal to 0. So when I look at the responses, then I would see the following. So I would always see a convergence to the exact desired value. So even if the system is underdamped like this, it's going to converge to the exact value, exact desired value here. So this is a type 1 or higher system. So for a system to give 0 steady state error to unit step input, its type should be at least 1. That is the main idea here. If its type is smaller than 1, like this, then it's going to give a non-zero, finite steady state error to unit step input. So now let us look at the steady state error to unit ramp input. Steady state error to unit. Maybe I should write it there. It's going to be easier to follow the same scenario. Steady state error to unit ramp input. Okay? In this case, we are looking at the ramp function, which is r of t is equal to t, increasing with slope 1. So in that case, what would be the Laplace transform of the input? R of s, it is going to be 1 over s squared in that case. Okay? And then I would apply this theory here still. Okay, let me try to apply it. So in that case, I would just have this s times 1 over s squared and the denominator, 1 plus g of s, h of s. So this s cancels one of the s's in 1 over s squared, and then I would have 1 over s divided by this thing. So this is going to be limit as s goes to 0, 1 over. I will multiply the denominator with s plus g of s, h of s, and I will have one more s here. Okay? Now if I take the limit here as s goes to 0, this quantity here, this s is going to go to 0, and I would have the limit of this multiplication s g of s, h of s as s goes to 0. So the result of this one is going to be 1 over limit as s goes to 0 s g of s, h of s. Okay? We are actually going to be calling this quantity again with another constant. And in this case, this constant is going to be called kV, 1 over kV. Okay? The earlier one was called kp, and this is called kV. All right? And the steady state error to unit ramp is going to be 1 over kV, and here kV is equal to limit as s goes to 0, s g of s, h of s. All right? And this constant has also a specific name in the control literature. So if g of s, h of s is position, what is s g of s, h of s? When you multiply a Laplace transform with s in Laplace domain, then you would get the time derivative in the time domain. If g of s, h of s is position, then s g of s, h of s is going to be velocity. Okay? Because it's the derivative of the position. So in that case, that constant is going to be called kV equals to static velocity error constant. Okay? So I can write here my new results. So the steady state error for to unit ramp is going to be 1 over kV, and kV is nothing but the limit as s goes to 0, s times g of s, h of s, and the name of kV in the control literature is going to be the static velocity error constant. All right? Now I can actually try to replicate this table for the steady state error to unit ramp input. Okay? So now I'm going to write the types here, 1, 2, 3, and I have kV here and the steady state error to unit ramp here like this. Now for a type 0 system, what is kV? Let me try to think about it. So here for a type 0 system, I don't have any s to the n term here because n is equal to 0. That is the type of the system. And this term is non-existent for a type 0 system. Okay? And here, what is the kV in that case? I will multiply this GH, open loop transfer function, with S, and then I will take the limit as S goes to 0. Multiply this transfer function with S and let S go to 0. These terms would all bring 1, and I have an S terms times K here. This term is still non-existent. Limit of K times S as S goes to 0. We see here that this limit is going to be equal to 0, so kV is going to be equal to 0 for a type 0 system. Okay? If a system type is 0, then kV is equal to 0. Then what is the steady state error to unit ramp input for such a system? I see that it is 1 over kV. If kV is 0, the steady state error would be infinite. Okay? 1 over 0, it's going to be infinite steady state error to unit ramp. So the response will not be able to follow the unit ramp function at all. The distance between the response and the desired input, the unit ramp, would be getting larger and larger, and the difference would go to infinity actually, okay? For a type 0 system. What about a type 1 system? For a type 1 system, I have here k over s and these terms. Multiply this with s, take the limit as s goes to 0. When I do the multiplication with s, that s is going to cancel this s and is equal to 1 here. And I would have just k and these terms. Take the limit of this thing as s goes to 0, it's going to be k. For a type 1 system, I have kv equals to k. And what is the unit steady state error to unit ramp input? It is going to be 1 over kv, so it's going to be just 1 over k. Okay? What about the type 2 system? For a type 2 system, I would have an s square here. Multiply this with s. S is going to cancel one of the s's in the s square, so I would end up with k over s here, and these terms. Take the limit as s goes to 0, this is going to be infinite. So kv is infinite if we have a type 2 system. And what is the steady state error in that case? 1 over infinity. It is going to be just 0. And if you try to do the same thing for the type 3 system, I have k over s cubed. Multiply with s, I will have k over s squared in that case. Take the limit as s goes to 0, it's going to be still infinite. And I would have 0, infinite, 0 here. Okay? So these are the steady state errors for different types of systems for the unit ramp input. Okay? Now let us try to visualize this once more. So I have this reference input R, and I am looking at a type 0 system. A type 0 system has infinite steady state error as time goes to infinity, which means that a type 0 system would not be able to follow the ramp at all. Okay? This difference would be going to infinity as time goes to infinity. Okay? So this is what a type 0 system response would be looking like. What about type 1 system? A type 1 system would have non-zero but finite error to unit ramp input. That means that a type 0 system would be responding something like this. So it has a constant difference, non-zero difference, between the unit ramp input and the response here. So this is the response, what the response would be looking like for a type 1 system. Okay? We have finite difference, finite non-zero difference between the response and the desired input, reference input. Okay? And what about the type 2 or higher systems? Those systems would be having zero steady state error. Okay? So a type 2 or higher system would be responding something like this. So they would start first getting away from the response, but they would converge exactly on top of the ramp response. So there would be perfect convergence at the end as time goes to infinity. So this is type 2 or higher. Okay? Of course here, I didn't assume any oscillations here in these responses. Sometimes you might have complex poles, complex closed loop poles in the systems, and then they might have the similar behavior, but they might be oscillatory. Okay, so I have this ramp input, and suppose that I have a type 0 system with some complex poles. In that case, the response might be oscillatory, and it might be converging, something like this, but this difference would be still going towards infinity. Okay, so this is type 0. And what about type 1? I would have a response like this, oscillating at first, but then converging to a constant difference. This is type 1. What the type 1 system would be looking like when we have complex poles for the closed loop system. And finally, a type 2 or higher system would be responding like this. It would oscillate around this value, and it would converge exactly on top of the desired value. So this is type 2 or higher. Okay? So far we have seen the steady state response to unit step and unit ramp. For a system to give zero steady state error to unit step input, its open loop transfer function should contain at least 1 over S. Okay? So I have here the unit step function. R of S is equal to 1 over S. Okay? And this is the unit step function. Steady state is equal to 0 for type 1 or higher systems. Okay? And R of S, for the unit ramp input, the Laplace transform is 1 over S square. Steady state is equal to 0 for type 2 or higher systems. So what does this mean? If I want the system to give zero steady state error to 1 over S, then the open loop transfer function of the system should contain at least 1 over S in its loop. Okay? And if I want the system to give zero steady state error to 1 over S square, the loop of the system, open loop transfer function, should contain at least 2 1 over S's. So it should contain at least 1 over S square. So this is really not coincidence. For a system to give zero steady state error to an input, that system should contain the Laplace transform of the corresponding input in its open loop transfer function. So for a system to give zero steady state error to an input like this, and that system should contain in its open loop transfer function, in its loop, the Laplace transform of that input. Okay? So the Laplace transform of unit step is 1 over S. For the system to give zero steady state error to unit step, we need in the loop I have at least 1 over S, which means this. So for a system to give zero steady state error to unit ramp, which is 1 over S square, in the loop there should be at least 1 over S square. Okay? This is always the case, actually. This is a very, very important principle in control. If you want a system to give zero steady state error to an input, you need to have in the loop the Laplace transform of that input in the system. I will just write this here. For a closed loop system to give zero steady state error to an input R of t, then the system should contain R of S, the Laplace transform of the input in the loop. Okay? And in the loop means it should be in the open loop transfer function. For unit step, 1 over S should be in the open loop transfer function. For unit ramp, 1 over S square should be in the open loop transfer function. For the closed loop system to give zero steady state error to those inputs. Okay? So the final thing is going to be a third type of input that we use in control, and that is called the unit parabola or unit acceleration input. These are the same thing. So I have either unit parabola input or unit acceleration. Okay? These are the same thing, and I will write here what R of t is. Maybe I should erase these. Unit parabola input is this. R of t is equal to t squared over 2. Okay? It is not t squared, interestingly. I will explain why it's not t squared. So if you look at the Laplace transform of this thing, it's an exercise for you. Please try to calculate this. It was one of the earlier or past exam questions actually. It's 1 over s cubed. Okay? So this parabola input would be looking like this. So that is the unit parabola input. So unit step is 1. Unit ramp is t, and unit parabola is t squared over 2. So unit ramp input is the integral of unit step input. Integral of 1 from 0 to t is t. Integral of t from 0 to t is t squared over 2. Okay? That is why we are calling this as unit parabola input. It is the integral of unit ramp input, and its Laplace transform is 1 over s cubed. Now if I apply this to the same theory here, it is going to be easy. I'm doing the same things over and over, but I think at this point you might be able to do it yourself, but still, if you are patient with me, then we can finish this. So I would have, in this case, s times R of s is 1 over s cubed divided by 1 plus g of s h of s. Okay, this s cancels the cube here and it makes it square, is equal to limit as s goes to 0 1 over s squared times this denominator, s squared plus s squared g of s h of s. And if I take the limit as s goes to 0, this is going to go to 0, and I will have the limit of this thing as s goes to 0. Okay? So I would have 1 over limit as s goes to 0, s squared g of s h of s. Now this is, again, another constant in control. And we call it this 1 over Ka. Okay? So it is the steady state error to unit parabola input would be 1 over Ka. And I would have here Ka defined as limit as s goes to 0, s squared g of s h of s. Okay? And what do you think the name of this constant would be? So in this case, the s multiplication is the derivative in Laplace domain. S square multiplication is the double derivative. GH is the position. If you assume that it is position, what is it? What is its second derivative? First derivative is velocity. Second derivative is acceleration. So this Ka is called the static acceleration error constant. Static acceleration error constant. Okay? And let us fill our table. I think you need to be able to answer the following question. What should be the type of the system B, for that system to give zero steady state error to unit parabola or unit acceleration input. What is the minimum type of the system that is necessary for a system to give zero steady state error to unit parabola input? What is that answer? And here I can use the same principle. For a closed loop system to give zero steady state error to an input R of t, the system should contain R of s in the loop. Okay? So R of s in this case is 1 over s cubed. So the type of the system should be at least 3 for that system to give zero steady state error to unit parabola or unit acceleration input. Now let us look at the cases. Type 0 system, I don't have this. Oh, here I need to change this. So this is Ka, and this is going to be Ka again, and this thing should be s squared now, and this I can erase just this one. So here let me try to fill in this table. So if type is 0, then I don't have this. Multiply this with s squared, and I would have here s squared times everything here. Limit as s goes to 0 will be limit ks squared as s goes to 0. So Ka in this case would be equal to 0. So, and what about the steady state error? It is 1 over 0, which is infinity. Okay? What about type 1 system? Type 1 system would have k over s squared here. Multiply this with type 1 system would have k over s, all right? And if you multiply it with s squared, then you would have k times s here and the other terms. Take the limit as s goes to 0, I would have 0 here, and I would have this thing infinite still. And what about type 2 system? Type 2 system would have k over s squared, multiplied with s squared, so the denominator and s squared cancels. So I would have the limit k, so ka is k, and the steady state error is 1 over k because of this. And for a type 3 system, I would have k over s cubed, multiplied with s squared, then I would end up with k over s here. And take the limit k over s as s goes to 0, ka is going to be infinite, and steady state error would be equal to 0. So you see here that for a third or higher type system, I would have 0 steady state error to unit parabola inputs. If you continue with the higher types here, you would end up with similar results. So as the type of the system gets higher and higher, the steady state error characteristics of that system gets better. So for low type systems, steady state errors would be bad. Okay? As the type gets higher and higher, the steady state error gets better and better. And we reach the perfect steady state error 0 if the type exceeds a threshold. And that threshold is determined by the input Laplace transformation. So here, let me try to draw the responses of different types of systems to unit parabola input. So this is the unit parabola input, and what would the response of a type 0 system be looking like? So it would be in that, I have actually forgotten which color I used for different responses, but let me use blue for the type 0 system. For a types, and I won't assume any oscillations, I won't assume any complex poles, so I won't draw the oscillatory responses here, because it's easier to draw non-oscillatory responses. For a type 0 system, the steady state error is infinite, and it would be looking like this. Okay? The response would be looking like this, so this difference between the response and the desired response would be going to infinity. For a type 1 system, the error is still infinite, but things should get a little bit better. So we still have an infinite difference between as the time goes to infinity, but since a type 1 system should be slightly better than a type 0 system, so the performance here is monotonically increasing here. So this infinity is probably much smaller than this infinity, okay? So I would have here, this would be looking like a type 1 system, and for a type 2 system the difference is now finite, and as a result I would have a type 2 system which is doing something like this, okay? So this difference becomes finite and it remains where it is. We are almost about to follow the response in that case. So this is a type 2 system response, what it will be looking like. And finally, if I want to have a type 3 or higher system, then I would have just perfect convergence to the desired response, okay? So I would have this type of convergence. So this is type 3 or higher, okay? So now I have finished all of the theory here. I will just finalize this issue with an example, which is going to be actually quite simple and is not going to take much. So let us say example. So we have the following proportional control system. I have K here, and I have 1 over st plus 1 here. So this is our system. The question is simple. I'm keeping a much more complicated example to the next lecture. So I have, what is the type of the system? And part B is compute steady state error to unit step, unit ramp, and unit parabola inputs. Okay? So I think it shouldn't take you much to solve this type of question. Okay? Now, what do you think the type of the system is? In this case, I will just look at the open loop transfer function here. The open loop transfer function is everything in the loop, GH. It is going to be K over, I have st plus 1. Okay? So what is the type of this system? It looks like a type 1 system to me. So this is a type 1 system. This is the answer of part A. So now let us look at the steady state errors to unit step, unit ramp, and unit parabola. So for that I'm going to calculate these important coefficients, Kp, Kv, and Ka. Kp is limit as s goes to 0 open loop transfer function. Instead of GH, I am writing here open loop transfer function. It's the same thing. So this is limit as s goes to 0, s times open loop transfer function. And this is limit as s goes to 0, s squared times open loop transfer function. Okay? Now when you look at the first limit here, you see that as s goes to 0, it is going to be, let the s go to 0 here, it's going to be k over infinity, k over 0, which is going to be infinity, and multiply this with s and take the limit, it is just going to be k, and multiply this with s squared and take the limit as s goes to 0, this is going to be 0. Okay? the steady state error to unit step is 1 over 1 plus Kp. And Kp here is infinite. Therefore, the system should give 0 steady state error to unit step input. It's a type 1 system. It contains the Laplace transform of the input 1 over s in its loop. Okay? So the steady state error to unit ramp is 1 over kV, and it is the kV is k. It's going to be 1 over k, and steady state error to unit parabola or acceleration would be just 1 over Ka, and Ka is 0, which means that the steady state error to unit parabola would be infinite. So then what does this system do? So to unit step input, its response is going to be looking like this. So this is unit step input. It should give 0 steady state error. If the closed loop system doesn't contain complex poles, the response would be looking like this, like an overdamped system. If the closed loop system would be containing complex poles, then I would have an underdamped response and exact convergence at the final value. So this is the response of this system because the steady state error to unit step input is just 0. Okay? What about the response to unit ramp input? This is my unit ramp. If the closed loop system does not contain any oscillation, any complex poles, then the response would be looking like this. Or sometimes we might have negative steady state error, so we might have something like this. Okay? It doesn't still contain any oscillations. If the complex poles exist in the closed loop transfer function, then we would have something like this. Or in the other case, we would have something like this. Okay? And finally, we have the response of this system to unit parabola input. And in that case, the steady state error is infinite. That means that my system would be doing something like this. So the response between the difference between the system response and the desired value would be going towards infinity. And finally, if we have complex poles, it might be looking like this. Okay? So that completes the theory and a very actually simple practice of steady state error concept. We're going to start our next lecture next week with a much more complicated example combining both the transient response characteristics and the steady state characteristics in our design. But that is going to be all for this lecture. Thank you very much for watching.